We're done with chapter 12, and today we'll be starting chapter 16. And the way chapter 16 is different from 12 is that it's essentially kinematic. So we're going to talk about velocities, accelerations, but we'll be talking about rigid body motion. So these things have dimensions; they are not particles, and this is much harder than chapter 12. So I want you to work hard and pay attention to this. So the learning outcomes from this class are understanding translations of rigid bodies. Understanding translation is just moving in straight lines. Understanding rotations, and then computing motion when things are rotating about a fixed axis. So motion, rotating about a fixed axis, and ability to analyze the motion of things which are connected, such as gears, pulleys, and basically they're connected either through just contact or through cables or strings. So the two things we'll do today are translation and translation. Translation is when things move in straight lines, they do not rotate. The orientation between this and this has not changed with time. So they can be what is known as rectilinear motion, and they can be curvilinear motion. Curvilinear is like this: when things move, they move parallel, but then they are curved. So you can move from here to here in a curved fashion, right? This is curvilinear motion. Rectilinear is when they move in straight lines like this, but there's no rotation. It's still translation. So the next thing is rotation about fixed axis. And the cartoon I have in mind is this is a body, this is the fixed axis, and that axis basically, so the body is rotating about that axis. So this is the axis of rotation. So if you consider a sort of a circle, because when this point here moves like so, it's moving in this fashion because the axis of rotation is this way. Any point would trace a circle, right? And that circle is drawn there. So if this particular point is here at time t equals 0, then it would have turned by an angle of theta degrees or theta radians, whatever you like, when it goes from t equals 0 to t equals some time, t prime. Okay, so just like we talked about using accelerations to compute velocities and positions when things move in straight lines, we can have the same thing for rotary motion. If omega is the angular speed, then that is simply the first derivative of the change in angle, theta. Similarly, alpha, so this is angular velocity, and similarly alpha is the rate of change of angular velocity, or d omega dt. That is called the angular acceleration. So this has a very similar form like linear acceleration and linear velocity. Another formula which is important, which is that, so this is analogous to what we did in motion in a straight line. You can also write alpha d theta is omega d omega, and this is similar to v dv is ads, right? This is the linear analog for this equation. So these equations are the key equations for rotary motion, and then you can integrate these equations just like you integrated the equations in when things are moving in straight lines to get omega is omega 0 plus alpha t. So this is integration of d omega dt equals alpha. Then you have theta equals theta 0 plus omega 0 t plus 0.5 alpha t square. This is the second derivative. This is integrating the equation for acceleration twice. And then if you take the integral of the third equation I wrote, alpha d theta is omega d omega. What you get is omega square is omega 0 square plus 2 alpha theta minus theta 0. So these are the equations for things moving in circles, or things rotating.
Professor?
Yeah.
Is angular acceleration constant in these cases?
Can't hear you.
Angular acceleration constant?
Yeah, acceleration, that's a good point. So alpha is a constant. This is not true if alpha is not a constant. So if alpha is not a constant, what would you do? You'd integrate. So what you would do is you'd go back to these equations right here, and then you'll put alpha, whatever is a function of time or angle, and then integrate. Don't use these formulas. These formulas are for constant acceleration. Okay, so two more formulas and we'll get to solving problems. So this is a 2D view, and this point here is, let's say P. The velocity of point P is omega cross r. Okay, now I'm assuming that this point here is at moving with zero velocity. Okay, so this is rotating about point O. This is only true when O is at rest, or O is the axis of rotation. Similarly, we can write a formula for acceleration. So acceleration has got two components, at and an. So acceleration is at ut plus an un, and the formula simplifies to a equals alpha cross r minus omega square r. Okay. Now again, as I said, O is at rest, O is axis of rotation. This is only true when the point O has an acceleration of 0. 0 velocity and acceleration. So later on we'll see that we'll do problems where I'll derive equations where point 0 or O actually has a non-zero acceleration. But this, as far as this part goes, we are assuming that it's at rest. Okay, so the last thing I want to talk about is how do you analyze things motion when it is constrained. So the typical examples are when you have gears, meshing gears, and I'm not going to draw gears because it's very hard to draw gears, but assume that there are gears and things are meshing. And things are actually rolling, so there's no slipping. Okay, when that happens, let's say this is RA, this is RB, omega A RA. So my question to you is, if A moves in the clockwise direction, like I've shown it here, it's clockwise because that's how the clock goes, right? Clockwise. How will B move? Will it also move clockwise, or it will move anti-clockwise? So remember that when two gears mesh like this, the other gear always moves in the opposite direction as the first one. So it's always going to move this way. That is assuming that they are not slipping. That's very important. They have their own, they have, the motion of A depends on motion of B in this case. They're not independent. Okay, that's why they move in this fashion. Now, how do you find the motion of B given the motion of A? So what you do is you look at the point P. This is point P, which is the point which connects the two. The velocity of P is, right from this formula, is omega A RA, right? Just if you see this figure here, velocity of P actually is in this direction. So that's omega RA, but that is also going to be equal to omega B RB, right? Just like I can look at motion of P from the fixed axis over here, I can also find the equation for motion of P based on the fixed axis over here. So what this means is I can now, given RA and RB, I can find a relation between omega A and omega B, which means that I can find omega B if omega A is given, or vice versa. Also, acceleration of P is alpha A RA equals alpha B RB. And the reason for writing only alpha A RA is because I'm only looking at the tangential component, AT. This is the tangential component. This is the normal component. Right? The tangential component should be the same. And that's why I get this. So again, if I know RA and RB, I can find alpha is a function of alpha B. Okay, is that clear? Okay, let's solve. Let's solve a question. Okay, so this question is, okay, a motor gives gear A an acceleration of alpha A equals 2t cube. So we know alpha A, where t is in seconds. If this gear is initially turning at omega A equals 15 radians per second, determine the angular velocity of gear B. So we got to find angular velocity of gear B when time t is 3 seconds. So solution, we need to find omega B when we're given omega A and alpha A. Now let's try to see how we can find omega B based on what we've done before. If we know if you go back, if we know the angular velocity of A and the radius, of course we know that, we can find angular velocity of B. So I'm going to write that formula down first. Omega B RB is omega A RA. We know what RA is, we know what RB is. We don't know what omega B is, and we actually don't know what omega A is. We know what omega A is at time t equals 0, right? This is at time t equals 0, but we don't know what omega A is at time t equals 3 seconds. So this is unknown. But if we get omega B, we'll be able to solve for omega. If we get omega A, then we'll be able to solve for omega B. So the question is, can I find the angular speed at t equals 3 seconds? That's what I'm after. How will I do that? So you can integrate. So you know the acceleration of A, it's 2t cube right here. So we can integrate that to get angular velocity of A, and once we get that, we can then use it to find the angular velocity at 3 seconds. So d omega dt. Okay, I'm not using the formulas I derived earlier because that was constant acceleration. In this case, the acceleration changes as time changes, so I need to integrate. So this is 2t cube d omega equals 2t cube dt. I want to integrate from omega 0, which is 15 radians per second, all the way to 3 seconds, and the time goes from 0 to 3. Right? I'll call this omega A. So I want you to try to get omega A yourself, but let me write it down in the interest of time. Omega A at 3 seconds is, I get it to be 55.5 radians per second. So once you get that, omega B is, from this formula, omega A RA divided by RB. Omega A is 55.5, RA is 0.1, so it's 100 mm, which is 0.1 centimeters, sorry, 0.1 meters, and RB is 0.175. So that comes out to be 31.71 radians per second. Okay, is that clear? Any questions on that? Yeah.
My question is initially WA is 15 reps per second. How come did you use a number?
It's right here. So I know the angular speed at t equals 0, but I want the angular speed at t equals 3 seconds. So I need to use the 15 to get the angular speed at 3 seconds. So this is angular speed at 3. This is the angular speed at 0. So if you are told to find the angular velocity of B at time t equals 0, then yes, you can use this formula. You shove in 15 radians and you'll get the angular velocity at B at time t equals 0. Any other question? Okay, let's see. Ample time. So I have time for one more question. Okay, let's go through this question. So you got to find the distance load W is lifted in 5 seconds using the hoist. The shaft of the motor M turns with an angular velocity of 400 times 4 plus t. So angular velocity of the motor is 100 times 4 plus t. We need to find h or height moved by W in 5 seconds. Okay. So the way I'll solve this is, if I can find so let's understand what's happening in this problem physically. When M turns, A turns. A is right here. That would cause B to turn, which will cause C to turn, then D to turn, and then E would turn. So moment E turns, all the string gets wound on the pulley. W would move up or down depending on the direction of M, right? So if I can find the angle by which E has turned in 5 seconds, then I can find what is the distance moved by W. It's simply going to be the angle turned by E times the radius of E, which is I think 50. So what I'm after is H is angle turned by E times the radius of E, which is 0.05 meters. So I need to get the angle turned by E. How can I get that? I know something about how m moves. M has a angular speed of 100 times 4 plus t. Okay, so I need to, well, let me find the angle turned by m, because if I know the angle turned by m, then I can perhaps use the formulas I derive for interconnected bodies to connect the angular speed turned by m in terms of angular speed of E, which I'm interested in. So angular speed of m is given to me. I can then relate it to the angular motion of m by this formula, right? The rate of change of angle is omega, and this is 100 times 4 plus t. So d theta m is 100 times 4 plus t dt. So time goes from 0 all the way to 5, and let's assume that the initial angle is 0. The final angle is theta m. It's an unknown. Okay, so I would like you to do this yourself. It comes out to be theta m comes out to be 3250 radians. Okay. Okay, so now I have this. My goal is to use this to find theta e. Once I find theta e, I can find h. Okay, and I'm going to use the fact that these bodies are all, m is connected to E through a series of gears. Okay, so let's start. Theta m is the angle turned by m. It's going to be the same as the angle turned by A, right? Because it's the same shaft. Now theta A is connected, the pulley A or the gear A is connected to gear B. So now I can use the formula I used earlier, which is I can relate the motion of A with B. So I'd written velocity is equal to omega r. This can also be written as, you can also write as, if omega r, in other words, omega r is a constant. If you actually integrate this, you can also see that theta r is also going to be a constant. So if theta r is going to be a constant, then theta a r a is equal to theta b r b. So I'm looking at a and b. So this gives me theta b is equal to RA divided by RB times theta A, but theta A is theta M. So theta M. Okay, so I know the angular motion of B. Now let me try to compute the angular motion of C. I'm going to work all my way like this, all the way to E. So B and C are in the same shaft, right? If they're in the same shaft, they'll have the same motion, same angular motion. So theta C is theta B is equal to RA divided by RB times theta M. Okay. So then I've got the angular motion of C. C and D are connected through a gearing, and I can use this formula now again. So theta D is just like this formula, it's going to be R C R T times theta C, but theta C from this equation is RC RD times RA RB times theta M. So now I know what the motion of theta D is, but I'm eventually interested in motion of E, but theta D and theta E are in the same shaft, so they would have the same angular motion. So theta D is theta E, so theta E is theta D equals RC divided by RD times RA divided by RB times theta M. And what you can do is use this into this equation here to get H. H comes out to be 2.89 meters. Okay, so please go through this carefully and try to get this answer. I will see you guys on Friday.